Okay, so let's start our proof of the lemma last time. So last time I just finished stating the lemma, but I didn't have time to prove it. So let me just restate it again. Okay. Yeah. So sorry for the repeating. Okay. So all right. So let me state the lemma. So yeah, I remember that I did a few definition like here last time, but I just can't write it, so I just started to state lemma. So I think we'll use the definition. So lemma, let gamma be a subgroup of the group of be a subgroup of the group of self-homomorphisms of a locally compact Hausdorff space X. Of a locally compact Hausdorff space X. So locally compact means that for any open set contains a relatively compact set. Okay. So no, sorry. So locally compact means that for every point and every neighborhood, there's a really compact neighborhood of that point in this neighborhood. So of the original neighborhood, yeah. Okay. So and then you have that. Okay, so then this gamma X probably discontinuously on X. On X, if and only if for each pair of points x, y in X, in X, there is neighborhood U of X. U of X and V of Y such that gamma U intersect V is not empty. Is empty for all but finally many element gamma of this V gamma. Finally many elements so let me try to understand this. So okay, the gamma acts properly discontinuously on X. Properly, okay. So what does properly discontinuously mean? Okay. Okay. So this means that so for every compact set K in X, K is compact, and then you have this small gamma of K intersect K is empty for all but finitely many element gamma of gamma, or big gamma, sorry. So only finitely many of this gamma of this K will have non-empty intersection with this K. Okay. So imagine all the images of this K under this gamma. Imagine all the images of this K under these gammas, different gammas, right? So only finally of them will have non-empty intersection. So maybe there are like many things that have empty intersection. It could be like uncountable maybe, but we know that only finally many of them has non-empty intersection. Okay, but finally many intersection. Wait. Many elements gamma of big gamma. Okay, so if and only if for each pairs of points x, y, and x. Okay. So here he is saying that if this gamma acts properly discontinuously, namely this condition is being satisfied, even only if each pairs of x, y, and x, there is a neighborhood u of x and v of y, such that, this gamma u intersect v is empty for all but finitely many element gamma of big gamma. Okay. Okay, so yeah, let me try to say the proof. Okay. Okay, so proof. Okay, so here, so if gamma acts properly discontinuously on, if gamma acts properly discontinuously, okay, and then this x, y, in x, so we basically what we do is that we fix a relatively compact neighborhood u of x and v of y. Okay, and then so if this Okay, so suppose this gamma x properly discontinuously, okay? So this is by our assumption. And then with this xy is in x. So now we let so now we let this u be a, so u contains x. Okay. Maybe I would say like yeah. Maybe I say that that u be a relatively compact neighborhood of x, and then v be a relatively compact neighborhood of y. Okay, and then okay, so basically we want to show that what? We want to show this small gamma. Okay. Small gamma u intersect b is contained in the set gamma of this closure intersect the closure. Okay. Sorry, the closure of u intersect closure of b. Okay, so these are like compact. Yeah, and the intersection is, wait, if a compact set, then if you have an intersection of a compact set and another compact set, then if you take any open cover of this set, then y is a compact set. Does it admit a finite cover for this one? Okay, yes, I think so, because if you pick, yeah. So because if for a compact set it is closed, right? Closed, and then I take okay, I think with an argument you can show that it's a compact set, right? Okay. I think this is true. Okay. So u union v, okay, is equal to empty set. Okay. Okay. And then okay, so for all but finally many elements, gamma, small gamma of this big gamma. Okay, so let's see why it's true. So yeah, I think by my argument here, because yeah, so namely because it's a nearly compact, so closure is compact, and then yeah, you have two intersection of two compact sets compact. Okay, I'll leave it to you to check. Okay, so if you have a compact set, so basically I think the key is that if you have two compact set, then you take any open cover, then you argue that so we want to pick a wait, hold up. So we want to pick a finite subcover that how do you do that? So if you have open cover, let's say that you have open cover for this neighborhood, right? So for each open set, okay. Okay, maybe as an exercise, okay. I think it's true, okay. So maybe as an exercise, we can show that, okay. So exercise. Okay, and then since it's compact, then okay, so we want to show the containment, right? So why is it contained? Okay, so basically for the containment argument, so containment. We know that for, so let's see, if we have x equal to this set, sorry, yeah, section x is in gamma u, which means that x equal to gamma of, let's say, y for this. Maybe let's use another letter, let's say x prime, where x prime is in u and then x is also in v. Okay, so that means what? That means okay. Okay, so y is it's probably discontinuity on x, even only if okay, so basically I think we want to show that basically we want to show that this so okay, so we want to show let's see, so we want to show that this x is in the image, right? So I'll probably discontinuous. Wait. Okay, we have to show that this x is in gamma of u intersect v, and also x is in. Of course, this is true, right? U closure intersect v closure, union v closure, yeah. So because x is in B, right? So sorry, yeah, because x is in B, so therefore this one, yeah, this one you identify, yeah. And then what about this one? So for this one, is this x prime necessarily? So this is in U, okay. Intersect the closure. Wait. So why this x is in this? Okay. Okay, so namely, because this gamma is a this small gamma, okay, this small gamma is a local, is a self-homomorphism, right? So therefore, for this one to be true, I have to show that namely this x prime is in U intersect V, right? So why this x prime is in U intersect V? So I definitely know that this x prime is in U, but why is but we only know that this x is in V, right? Okay, so why x prime? I know that this x prime is in U, but shoot, I made a mistake here. So this one is union. Okay. Okay, so here we go. So so should, yeah, okay. Okay, I think if it's a union, then I think it's obvious, right? So because if you take the union of these two compact sets, so then it's also compact, right? Because if you take any open cover, then you can pick a finite subcover relatively to this first one. It's open cover of this one, of this if you take a open cover of this union, right? So of two common set, then it's also it's also open cover of this K and K prime, and so that you can pick a finite cover of this one, and then you pick a finite cover of this K prime, then the union is finite open cover of this one. Yeah. So okay, but yeah, okay. So and then okay, so then yeah, so I think we have this property. Okay, I think we have this property. So then yeah, we do have this property actually. Okay, so what's next? So because okay. Okay, so we show this containment, right? So and then okay, because this gamma is because this, by our assumption, this bit gamma is x probably discontinuity, and then so therefore this is a compact set. Okay, so then compact discontinuity means that for any compact set, right? For all compact set, okay. So this is a compact set. So therefore, so therefore you have this. Yeah, you have the property below. Okay. Okay. and okay, so then so then oh, okay. So I think this finished the proof of this forward direction, right? The proof of the forward direction. There is a neighborhood u of. Okay. Okay. So now let's prove the sorry backward direction. Okay. So what is the backward direction? Okay. Okay, so now suppose that K in X is compact. Okay. So suppose that K in X is compact. And that for each pair of points x, y in K, and that for each pair of points x, y in K, there is neighborhood u x y of x and v x y of y such that neighborhood u of x y of x and v x y of y such that is set g of x y defined to be the set of all small gamma in this big gamma such that small gamma of u x y is like the v of x y is not empty. Okay, it's finite. And then for okay. Oh, okay, I see. So and then for each pair of points x, y in K, there exists neighborhood u x y v of y x y such that for each pair. Oh, okay, okay. Yeah. So because we are going in the backward direction, right? So we can do this assumption. Okay, but okay, and then for each pair of point x, y, k, there is a neighborhood u of x, y, v of x, y. Yeah. Okay, and then such that yes. Okay.
yeah, so basically this is so that this g of xy is which is given so g of xy is being defined as all the non-trivial intersections. All the gamma that means that this intersection is not trivial. The gamma of uxy and intersect with the v of xy is not empty. Okay, so the all non-empty intersection. So the all gamma that realize this non-empty intersection. So that this intersection is not empty. Okay. Which is finite because it is empty for all but so it is empty for all but finitely many elements. Okay, so it's empty for all but finitely. Okay, I see. Okay. Wait, why? It's non-empty intersection. So it's empty for all but finitely many elements. Empty for all but okay, it's true. Okay. All right. So what happened next? So okay, so this is our g of xy, right? So what do you want to show? Okay, maybe I want to continue with the. So now, for each set x in K, each point x in K so we may choose a finite set yx in K a finite set yx in K. Okay, such that this K is contained in the union of such that this K is contained in the union of the y in this yx. Sorry, this is yx of vxy. Okay. Okay, so let's try to understand this. So, for each point x in K, we may choose a finite set yx in K. Oh, I see. Okay, yx such that this K is contained in. Oh, I see. Okay, so in the set of all y in. Okay, so this yx is like an index set. Okay, so it's the union of y in yx v xy. I think the idea is that basically, if you choose, okay, let's see. Wait. Okay, let me think. So I think the thing is that, right. So if you choose, so basically, let me draw a picture here. So here you have the K compact set, right? I'll just use a I just use the rectangle to show that. Okay. So you have point x. So basically, I know that for each point x, right? So for each pair of xy, we can choose this v of xy and the u of xy. Okay. So and then, so basically okay. So what I do is that. So but what I'm a little bit worried about if so if for any neighborhood of y, if you are taking this neighborhood like v of xy, right? So does this so why does this it's an open cover of K? Right? So it may not be an open weight. Okay. G of xy is okay. Wait. Okay, I was a little bit confused here. So, I mean, can this xy be the same? I mean, like, if you take x equal to y here, okay. There is this symbol for u of x and v of y such that this is equal to mt. What do you mean by pair of points? You mean they are distinct points or they are the same point? Okay, so it's y in this finite set. Okay. I think the thing is that if you have, let's say, x equal to y, right? Okay, so let's see whether this will apply for x equal to y here. Oh, okay. Okay. Okay, yeah, I think when x equal to y, okay, you have the u and v, they could be the same, right? And then what you have is that yeah, you will have this gamma u intersect v. Yeah, I think it will still hold, right? Because this u and v, we don't have any restriction on this u and v, right? So if these u and v, they are the same, so yeah, so same argument. So if you are the same, okay. Okay, so this is always true, right? So we don't use anything about this x and y. We just take this x is not this x. So yeah. So this argument, this containment argument is true for in general, right? And then we have this. Yeah, I think this argument also holds for this x equal to y. Okay. So and then. Okay, I think what he means is that, so basically what you do is that, yeah, so basically you choose, yeah, so you can choose the same point. So after you choose the same point, you form the same neighborhood. Okay, after you form the same neighborhood, yeah, so this vxy is equal to uxy. Okay, just different names. Okay. Okay. All right. Yeah. Yeah. So you just choose the x to be contained in this y. Okay. I think that's all. If you choose x that's contained in this y, then this v of xy is equal to the u of xy, right? Okay. Okay, yeah. Okay. Yeah. So this is true. Okay. And then what happened next? So so that is k. Okay. Yeah. So yeah. You can do that. Okay. So these are open cover and then finite cover. Okay. And then and we may okay. So and then we may set this wx equal to the neighborhood intersection y in this y x u x y. Okay. Okay. Okay, so remember this one is like the yeah, this one is like the counter one, okay. And then yeah, so because for each v of xy there it is as u of xy, that's the neighborhood of x, right? So basically, yeah, these two is not necessarily destroyed, okay. And then wait, yeah, here we're just saying that it's like the neighborhood, right? We don't say that it's a destroyed neighborhood.
nothing. Yeah, there's no assumption about any destroying, destroyness, right? Gamma unit. Okay. But what happened with gamma? Okay, I don't see any destroying, but the thing is that this u of xy, okay, this u of xy is a neighborhood of x. That's the thing I'm sure. Okay, and then if you take the union of y, then it's gonna be a neighborhood of also a neighborhood of x. Okay. Okay, so this is a neighborhood. So it is open. Okay. Okay, so and then so thus oh, okay. Okay, so yeah, so basically for each x, I can do that, right? I can find a neighborhood of this x. So basically, I do this for any x. That gives a power. That gives a cover of this k, right? So after that, after you have that cover, you can get a finite sum cover. Okay. So this is the idea. So therefore, there exists what? So there exists So therefore, I can say that there is like a x1, xn in this k, such that this k is like contained in the union j equal to 1 to n wxj. Okay. All right. So if gamma is in gamma and gamma x is in y for something else. Okay. Wait, what? Oh, okay. Okay, so here is a interesting argument. So, oh, sorry, yeah. So this is a similar. Okay, and then maybe I'll just sneak it here, and then okay, so if we have this small gamma is in this big gamma, and then this small gamma of x is equal to y for some xy in k, then